Hello everybody, welcome back. Whereas we have a lot to talk about logistically, I thought maybe we would start mathematics. And so here's what today's about. First off, that's the chapter we will be doing. It should take us at least into April. It's chapter 9 in our textbook. Today we'll be doing infinite sequences. Maybe only half of it, by the way, though I don't think we're going to get to the squeeze theorem. Here are some exercises for you that at the conclusion of today's tape, I'm hoping you diligently work on those. Okay, so let's go. As I said, chapter is called Infinite Series, and we're doing infinite sequence. And a sequence, just by definition, it's just an ordered array, ordered array of numbers. Array of real numbers. And it's just a list of numbers. Essentially, it's a list. It's just a list of numbers. This word, by the way, means we count these ordinally. I'm not exactly sure what that term might be in other languages, but in English, ordinally means these numbers: first, second, third, nth, etc. The 75th, the 100th, any one of them we can name. Note there's a one-to-one correspondence between the ordinal numbers and a sequence. Every number in a sequence has an ordinal number associated with it. So here's the way we denote sequences. Denote. That's the set whose members are, at least that's the way I always read it as, A sub n. And we want, that's how you would denote the thing, and then we want to go from n to, say, 1 to infinity. This will include the first term. This n doesn't have to be 1. We can start at the 8th term, so then be 8th to infinity, and for that matter, we can stop it before it reaches. So that's how you denote it, and there's ways to delineate. One is you just list them. You just make a list of them. 1, 4, 7, 10, 13, 16, etc. That list has to be long enough so that the user of the list can understand that there is a pattern there. 2, you can use an explicit formula. In this case, A sub n equals, let's see, it's 3n minus 2 for n greater than or equal to 1. Or you can use what's called a recursion formula, where you list the first one. A sub 1 equals 1, and then A sub n, where are we? A sub n is, well, equals A sub n minus 1 minus 3. Plus 2, for n greater than or equal to 2. The first one's 1. The second one is 1 plus 3 is 4, etc. So there's 3 ways to list them. And so, just as an example, just one example before I erase this board. Well, I'll erase some of it. Example, let's just list the terms. Oh yeah, I'm doing this one for a reason. N plus 1 over n. There we go. And all I want to do, let's list the terms. Now, of course, we're going to work calculus on these things. But all I want to say is let's list the terms. For n is 1, that's 2. For n is 2, 3 halves. For n is, where are we? 5 fourths. For n is 5, right? 6 fifths. That's it. We just listed the terms. We took a recursion formula and we listed the terms. So that's an example of one way we work with them. Notice it appears that this is converging. Looks like it might be getting closer to 1. We'll talk about that in a second. I'm going to erase and start over. Erase everything. All right, everybody. That was our example. Turn the page. We're getting to convergence, I think, right now. I think I just mentioned the word convergence. Let's look at this, for example. A sub n is 1 over n squared. Now, I think you could just see, right? 1/4, 1/9, 1/16. You say, hey, what's going on there? This series will, this sequence will converge to 0. So what does that mean, that it converges to 0? Generally. Convergence to a limit means we can make the latter numbers of the sequence as close to the limit as we want. Convergence to a limit L means that for n as big as means for n a sub n where n is big, you can be arbitrarily close to that L. Here's a picture of this one. I think I have this one. Yeah. Okay. Here's a picture of the function's value. Whoops. Yeah, the function's value. 1 over n squared. It starts here. 2, it's way down here. 3, it's at 1/9. The picture of the function is continuous. The picture of the sequence is not. It's just these points. The points. This discrete mathematics. So what we're saying is, here is L. L is 0. This one right here. We're saying that I can take any number at all that I want and call it epsilon. And on either side of that limit, this could be as close as we want, and as long as you go far enough out, we will be within that distance forever for the rest of the sequence. If that's the case, then we say the limit is L. Formally, I guess I have to get this down. The sequence. Oh, okay, the definition. Definition of convergence. The sequence. A sub n, and goes to infinity. Converges. F to an L, F converges to a limit. If and only if you are given any number, arbitrary, and we're calling it epsilon greater than 0. We're given any number epsilon greater than 0. I always I make 2 different kinds of epsilon. Epsilon's greater than 0. Then if you're given any number at all, then you can find, or there exists, a number. We'll call it capital N, such that, for which the absolute value of A sub n minus L is less than epsilon for n sufficiently large. formal definition. Delta epsilon, well, it's not a delta, but it's actually an epsilon definition. Delta epsilon definitions are something that's coming soon. Definition convergence. Let's see where my note card is. Can we stop right now? We're in the province hall. Yes, stop.